Hello, welcome back to Water Logic. This is part two. So this is the table of contents from last time. We covered water mechanics in the first part, and now I'll cover the mechanisms. So that'll be pretty much doors, bridges, floodgates, levers, pressure plates. I'll talk about mechanism, state, and signals. Signal timings, which is a little bit of a complication in all of this. So what problems um, it causes, and then we'll talk about the designs around it. I'll get to components or composite components next time. If you've been following since the first part, I've changed the title of the third section. Previously it was called devices, but that could be confused with what the wiki calls devices, doors, hatches, grates, etc. So I'll be just calling them composite components. All right, so part two, mechanisms. So I'll start off with doors, bridges, and hatches and floodgates. So devices. So the full set of devices includes doors, hatches, floodgates, grates, supports, bridges, gear assemblies, restraints, cages, spikes, bars, and track stops. So all of these can be hooked up to levers and pressure plates to impact their state. All devices, right, can be configured to accept signal inputs, right, and they have a binary state of the following form, right? So you can think of them as on off or open closed or active deactive or disengaged engaged, right? So the language is varied in terms of how we describe or how the wiki, Dwarf Fortress wiki describes state. Depending on the device, right, different languages used on the wikis. So to simplify things, we're just going to think of them as having, one simple state and signal, right? So we're calling it on off. All right, so some devices are one-time use, like cages and supports, but we'll just ignore this functionality for the time being, right? So just assume we are, all these things can be repeatedly used, right? So the devices the devices we care about are going to be these four, right? So doors, bridges, hatch covers, and floodgates. So these are capable of blocking the flow of water, right? Either on a horizontal level or on Z levels, right? So input devices, right? So technically, levers and pressure plates are also devices, right? So like the other devices, they have state, right? They have a binary state. You can think of them as on and off, or being on or off, right? So instead of these input devices accepting signals, right, they send them when they change state, right? So rather than state changing when they receive a signal, input devices send a signal when their state is changed to all the quote-unquote output devices that are linked to them. So these output devices, right, doors, floodgates, hatches, etc. All the things that can change state due to a signal. Right, so the input devices are pretty much the opposite of the quote-unquote output devices in that they send a signal when their state is changed, right? And it's kind of the inverse for the output devices, right? Their state is changed when they receive a signal. All right, so the mighty lever, right? So the lever is the only device that lets us generate a job that'll send signals, right? So it's the only the only device that we can have our dwarves directly create signal changes, right? Which is pretty useful, right? So it's extremely useful, but also has some problems we might need to design around. So the lever. All right, so the lever is two states, right? On or off. When the dwarf pulls a lever, it changes state from either being on to off or being off to on, right? So if it's going from on to off, it sends an off signal. If it's going from off to on, it sends an on signal, right? So the state it's going to sends that same signal. Here is some levers, right? So this is a lever. On the right is off, denoted by this red flooring, right? And to the left is on, denoted by this green flooring, right? So I can pull the lever, right? This will generate a job that a dwarf will come and do, right? And when the moment this is executed, it's going to go from its off state to its on state and send an on signal. Okay? So we'll look at this in a second. Let me just cancel this. Lever's two states, on, off, right? When it goes into a state, when a dwarf pulls it into its on state, it sends an on signal. When the dwarf pulls it into its off state, it sends an off signal. Off signal would, close a door, and an on signal would do the inverse and open that same door. Okay. All right, the next input device is the messianic pressure plate, right? So pressure plate's extremely powerful. Just like the lever has a state on off, and it sends signals, right? Exactly like levers do, right? Well, except for the fact it's triggered by a dwarf, right? Except that the state change for the pressure plate is conditional, right? So it changes state when some condition is met. All right, so there's three conditions. We are just going to care about you know, one of these for the purposes of automation. I guess two, the creature weight is also useful. We'll use it in long timers, but for all the other stuff, right, we only really care about water and magma level being the condition being met, right? So for our automation purposes, we only really care about this first condition, the water magma level. All right, so for the pressure plate, it also has two modes, right? You can have a one-time use pressure plate where as soon as it's like triggered through this process, it'll, I think it deconstructs. I'm uncertain though. I don't really use them much, but yeah, make sure you're not using the one-time use pressure plate mode. All right, so let's talk about the trigger conditions on the pressure plate. So when it's created, the pressure plate must have a condition specified. Let me just show you that. Let's just go and build a pressure plate real fast. It's in traps at the very top. And you can see right here, there's this setting here. And we've got one-time use, we want to use resets. And we have 4 conditions. Water, magma, minecarts, and creatures. So we'll talk about creatures later. I'll ignore minecarts, and water and magma are functionally the same. It's just what kind of liquid triggers it, right? Here's we've got water, right? And we have some depth specification that we can do here. Okay, so we need to declare a range from 0 to 7, and the range represents depth, right? So on the left is going to be the minimum value, and on the right is going to be the maximum value for the condition to be true. Let's look at this here, right? So top right up here, you can see the minimum condition is going to be the left, right? And the maximum condition is going to be right. So if I was to make this right now, this pressure plate would be, its condition would be true if the water level on it was between 1 and 4, right? So we can change this, right? We can do 2 and 4, or 3 and 4, or just 4, right? We could also have like just 0, right? Or we could have, 2 to 7, for example. So if the water was above 2, right, then it would activate, right? This upper bound here, 7, pretty much just means that the maximum water level 7, right, it won't evaluate to false, right? So if our pressure plate is off, the whatever condition that's supposed to be pushing it down is not true. Like let's say our pressure plate is 2 to 7, right? So if there's 1 or 0 depths of water, if there's no water or 1 water on the tile, it'll be false. Every other case it'll be true, right? So let's just, I'm just going to place this pressure plate like this. Right. We'll just put it there for reference. Right, so if the pressure plate's off, if the liquid inside inclusively the specified bounds, right? If the liquid is inside the specified bounds, then it'll change state to be on, right? And inversely, right, if the state is on, if the liquid is outside the specified bounds for 99 ticks, and this is important, right? There's a time component to this, right? Then it'll change state to be off. If the pressure plate's off, it's going to continuously check if the water on top of it meets the condition. If it does, it will change state, right? And if it's on, right, the pressure plate will continuously evaluate whether or not its condition is false. And if it is for 99 ticks, it will go to the off state. A few examples. So let's look at example 1. So a pressure plate with condition of 3 to 7, right? So if it's off, it'll transition from off to on when the water is greater than depth 3, right? So 0, 1, or 2, it won't do anything, right? 3, it will transition to on immediately. And if it was on, right, it would transition to off after 99 ticks if the water level is less than 3. Right? And the second one, right, we've got a pressure plate with a condition of 0 to 0. Right? So you see 0 to 0, right? The minimum is the maximum, so this pressure plate would only evaluate to true if there was absolutely no water on the tile. So 1 water to 7 water, it would be false, right? So right, so you can see this pressure plate, we set it to have a range min max 0. So as long as there's no water on this tile, this pressure plate will be pushed, right? And because there's no water on this pressure plate and it only activates in between the range of 4 to 7, then this one will stay inactive. Okay. So for the second pressure plate, which is the one I just placed, right, we'll transition from off to on if the water is equal to 0 depth immediately, right? And inversely, right, it will transition from on to off if the water is not equal to 0 depth for more than 99 ticks. Okay, and this last one here, last example. So the pressure plate with a condition of water 2 to 6. All right, so we'll transition from off to on when the water is between 2 and 6 inclusively, immediately. And it will transition from on to off if the water is less than 2 or greater than 6 for 99 ticks. Okay. So something to note, so water at depth 1 will stay for a really long amount of time. So you got to be careful when using condition 1 or 0, right? As they'll probably be triggered by the pressure plate for a long time while the water is evaporating, if there's water that ever gets onto it, right? So water evaporates at 1 height, and so a pressure plate with a 1 height water detector is going to be pushed down even if the water's 1 high evaporating on it, right? So I guess all I'm saying is if we're trying to do logic with flowing water, right, we gonna have to be careful about this one edge case where one deep water doesn't flow anymore. Okay. All right, so pressure plate state and signals. So the pressure plate, similarly to the lever, has 2 states. It has an on state and it has an off state. All right, so looking at these two, right, I can't zoom in anymore, but this pressure plate is on, right? It's pushed down, and this pressure plate is off. It's not pushed down. You can see it's like this one's slightly darker than this one. It might be easier to see on non-obsidian mechanisms, but here we are. All right, so on state, when the condition is not met for 99 ticks, it goes to the off state. All right, and the on state, immediately when the condition is met, it goes to the on state. All right, so the transition from off state, transitioning to the off state and sends an off signal to all the connected devices, right? And in this case, when it goes from off to on, it's transition from the on, it transitions to on state and then sends an on signal to all the connected devices. Important part about this is this 99 ticks, right, before the false condition is accepted. So right, the activation condition must be false for 99 ticks before a pressure plate can change state from on to off. Right, so off to on is immediate, whereas on to off needs 99 ticks for the condition being false to deactivate. All right, this can cause some slight problems that we need to design around. This was probably implemented by Tarn to stop pressure plate state from spamming signals to all connected devices, which should probably lead to state desync fairly quickly. All right, so we'll talk about state desync in a little bit. It's one of these, it's one of the problems we're gonna have to design around, I guess is the best way to say it. Okay, so we talked about the input and output devices, right? So all this stuff up here. So let's talk about mechanism state versus signals. So mechanism state. All right, so let's look at the door real fast. So, doors, when you place them, they're not, and they aren't linked, right? They can be opened by dwarfs, but as soon as you link them to an input device like a pressure plate or a lever, they will be barred, right? And there'll be like a piece of wood across the door, and the dwarves will no longer be able to open them manually. Instead, they need to be controlled with the lever pulls or pressure plate presses, right? So an the on state for the door is open, right? It'll allow water to flow on the same Z level, right? If it's sent an off signal, it will change state. It will close the door, right? So if you imagine a lever being on and turned to off, which sends an off signal, right? The door can accept this off signal and will change state to be off. An off door is closed. It will block water flow horizontally, right? And if a lever goes, which is attached to it, goes from off to on, which sends an on signal, right? It will open the door. So let's just look at that in action. So I have a door right here. So here's our test door, and it's linked up to this lever, right? So I'm going to pull this lever. Notice the door is barred here. You can see the piece of wood over it. You can see here it says operated by mechanisms, which means we can't, like this door here, I can bar it, right? If I wanted to, I can bar it manually, and when it's open, dwarves can pass through it. But in this case, because it's linked to this lever right here, it's barred and can no longer be manually opened by doors. All right, so I'm going to pull this lever and move it from an off state to an on state, right? And it should open this door. So At here is going to pull this lever, and you can see immediately the door is open, right? It allows passage through right now, and you can see how immediate that was, right? The second you pulled it, the door opened. All right, so there is a problem and a complication, right? So sending an off signal to a door in the off state does nothing, right? And similarly, sending an on signal to a door that's already open does nothing. Important thing to notice is that we aren't sending a signal that toggles the state of the connected devices, right? But instead we're sending on and off signals that change state only if they aren't already in that state. So there's one key exception to this, which is the gear assembly, which legitimately does toggle, right? That's how it functions. We're going to ignore it in this water logic, in the context of water logic, because it's not super useful, at least as far as I've been able to find, right? So all the devices only change state when they receive the inverse signal, inverse to the state they're in, right? So just to rephrase, right? A door that's on, right? If it receives an on signal, nothing happens. It's already on, right? If a door that's closed, off, receives an off signal, nothing happens, right? It's already closed. So we can actually look at this. Right, so this door is open, caused by this lever, right? But I have this second lever, which is also linked to this door, right? It's also linked to the door, and I'm going to send the door an on signal here, right? So we're going to hit this lever. It's going to go from false, or it's going to go from off to true, or off to on. And you're going to see the door, nothing's going to happen, right? It was already on, and so an on signal does nothing to it, right? So we're going to hit the first lever again, and notice it's going to be going from the left, which is on, to the right, which is off, and that should send an off signal to all these devices, and you see the door close immediately after being hit, right? So in the exact same way, if I hit this second lever, right, and sent another off signal, the door's already closed, it's not going to do anything. All right, nothing has happened because the door was already closed. All right, so this is like a minor complication when we are designing devices, and that's simply that, you know, we're not toggling states, we're not guaranteeing something occurs when we send a signal. It is kind of limited, right? Devices, nothing happens if they receive the wrong signals. All I'm saying, right, minor problem we need to design around. All right, so let's look at another interesting, useful device, and that's the hatch cover. So it's pretty much the same as a door, except instead of limiting horizontal flow of water, it can limit the vertical flow of water. So an on state will allow water to flow vertically, right? And if it receives an off signal, it will change state, right? So if a lever goes from the left to the right, when it's in the on state, it's going to close, just like a door. Similarly, the off state, right, is closed and blocks water vertically, right? And if we flip a lever on and send an on signal, it will open the closed hatch cover. All right, so here it is. Here's a hatch cover, right? So similarly, these two levers are also hooked up to it. So we're going to have a dwarf pull this lever, and you're going to see the hatch cover open when it's sent an open signal. All right, immediately, like the door, it has opened. So I've sent a made another job for this lever, right? And the lever is on, right? It's pointing left. It's in the on state. When I hit, or when this dwarf, when at here hits this lever again, it's going to send an off signal, which will close this hatch cover immediately, like so. All right, so You could think of hatches and doors as being pretty much having the same behavior, right? Except one is just blocking kind of this horizontal movement of water, whereas the hatch cover is just blocking water moving z levels through it, right? So it also has the same issue, right? That same problem as the door, and that's that it can't, or nothing happens if you send it an on signal and it's already on, right? So, okay, I've got this second lever selected. I've got a job to pull it, right? And we're essentially going to be sending an on signal to these devices, and you can see this hatch cover is already open, so nothing's going to happen, right? And if we pull this lever, right, it's already on. We sent it an on signal, nothing happens, right? So we're going to pull this lever again, sending an off signal, closing it all, right? And I'm going to pull this first lever here, which is on, to off. We're going to send an off signal, and we're going to see an off signal when it's off, does nothing. Right, like so, nothing's happened. Expected behavior, okay? All right, so what do doors and hatch covers let us do? Well, like right away, we can control the flow of water, right? So in the horizontal direction with doors, right? So the 8 horizontal directions. And this also lets us control the vertical direction of water flow with the up-down, with hatch covers, right? So we can send them signals in 2 ways, right? Either based on some condition, like pressure plate conditions, right, and water depth, or we can have our dwarves generate signals with pull lever jobs. The good thing about doors and hatch covers is there's no signal delay, right? They immediately get enacted, except in the case with the pressure plates off condition evaluation taking 99 ticks. Now, it should be noted, right? This 99 ticks is from time between the condition being, true and the signal being generated. Right? So, let's say we had a pressure plate testing if a room was empty of water, right? 99 ticks after the room is empty of water, the signal will be generated. There's just a kind of delay in the off state condition evaluation of the pressure plate. That's all I'm trying to say, right? We got to be careful of that. So, we can control the flow of water already. Like, what are we missing, right? Using these, we can already create some interesting components, right? So, for example, I have a very simple water logic setup right here. So, right, you can ignore these doors. They don't mean anything. They're just for access. My dwarves get in through here. They come down and come through here. These are just kind of to stop the flow of water, right? So my dwarves will come in through the fort, come up this stairwell, down through here, through this airlock system, which you can see there's a diagonal. I won't talk. Anyways, my dwarves come in through here, and this chamber is flooded with water, right? So this is a simple latch under this hatch cover. So this will be flooded with water, and the water will be able to fall down into this area and be depressurized. It'll go diagonally into this small 2x1 chamber where there's another hatch to drain it and a pressure plate to read whether or not there's water in here. So this is a simple latch, and all we've used is this hatch cover, right? You can imagine some alternate setups using doors. I could probably do it, but hatches are pretty much ideal in this scenario, right? So this is a latch. Essentially, water will flow down here, be depressurized, fill this chamber, and then, all right, this pressure plate will, do something, and then we can, close the entrance leading in, and we can open the exit, and that'll drain it, and then cause the pressure plate to evaluate to false, right? So we can already make what I'll later call a latch with just these two. So we're kind of halfway there, right? But we still need some functionality, right? Which we can achieve with bridges and floodgates. Right, so like I was saying, right, we can already make latches and consequently short timers, which are pretty much just latches hooked up in a specific way. What are we missing? Well, we can't easily do signal inversion, so negation, right? So we can't turn an on signal into an off signal or an off signal into an on signal like there's not some trivial way to turn our hatch covers or doors into like an inverted signal, right? It's just we don't really have the tools yet. All right, so let's talk about bridges. So bridges are pretty useful. So there's kind of two kinds of bridges, right? We'll call our kind the normal bridge, which I think is like a drawbridge. And then we also have retractable bridges, which when they're in their on state um, are fully retracted and have like they don't block any space, whereas the retractable kind, or rather the normal kind, the drawbridge kind or whatever, group like block an area when they're pulled in. So retractable bridges function pretty much like hatch covers, right? So their only difference is that they have a slight delay increase or included, right? So there's a delay with bridges. We could use bridges like hatch covers if we just use their retractable version, but there'd be a slight delay. So we'll kind of ignore these for our water logic purposes, right? We'll ignore the retractable bridges for our water logic purposes. Yeah, we're just going to assume they're in kind of this one-by-one form. They can be made bigger. It doesn't really affect their state properties at all or how they behave, right? So um, you can see here's a bridge. This is the bridge we're using for testing purposes. It is in its quote-unquote one-by-one form, right? It's just kind of open right now, right? So this is it in its off state, right? So in an off state, the bridge is open, right? So it's going to let water pass, through this space in on any of these 8 directional axes. Water could flow over it when it is in its off state. When it's in its on state, right, it's closed, right, and it's going to block water from passing. All right, so let's pull this lever. So we're just going to pull lever and trigger it to change state from off to on. All right, so lever is pulled and some ticks later it closes. You can see it already has kind of the opposite behavior of the door, right? When the door is in its on state, right, it allows water to pass through, right? But when the bridge is in its on state, it blocks water from passing through. So it's kind of already behaving as kind of an opposite of the door, right? The only difference is its delay, right? There's a delay between the moment it receives a signal and the moment it actually changes state, right? So I believe we'll look at it in a second in any case. So, right, so I hit the lever, I sent in an off signal. We lowered our drawbridge, right? This is the off state for the bridge. All right, so important, right? Bridges, unlike doors and hatch covers, have a delay after they receive a signal, which they can accept before their state is changed. Right, so something I skipped over, right? The bridges, just like doors, right, and all the other output devices, right? They can only accept signals that will change their state, right? So here I just sent this on bridge, an on signal, right, and nothing happened, right? We need to receive the opposite signal as the state to change their state, right? So here we're pulling the lever again, sending it an off signal, right? And I'm going to send another off signal. We're going to pull this lever from on to off, right? And you're going to see the bridge is not going to change state at all. All right, so nothing's happened, just like all the other devices. There's a 100 tick activation delay before bridges will have their state changed if they accept that signal. So this can cause some problems if we don't design around it. So bridges state can easily become desynced from a lever state if you spam pull commands fast enough. So let me just show you desync. All right, so to cause this desync, we're just going to pull the lever on repeat with our, we're going to make it important. So the idea is we sent a signal, we sent an on signal, right? The door and the hatch cover immediately opened, but the bridge is still processing that signal, right? It's probably got like 50 or so ticks left before it's going to close. And if we can send another signal, let's say send an off signal, while it's still in the off state, waiting to be transformed on, then that off signal is going to be ignored, and we can get the lever and the bridge to have opposite state. So we're just going to spam the signal for a little while, and eventually someone's going to be able to achieve this. All right. So they're all off. She's sending an on signal. Okay, here we go. She sent an on signal, which opened the bridge and the hatch, right? The door and the hatch cover, right? The bridge is still processing its on signal, right? So it's still in the process of turning on. Now she's going to hit this lever, sending an off signal, which closes the hatch and the door, but the bridge was already in the off signal, or in the off state, and so the off signal is ignored. Now there's still a floating on signal, which the bridge read, and so in a moment or two, let's mute this. All right, so this is no longer going to get pulled. Now, right, so there's a floating on signal. The bridge is still in the process of turning on, right? But we sent in an off signal which was ignored. So let's see, right? So yeah, like I said, the bridge has transformed into its on state, but you can see the lever is in its off state. So right, so lever's off, the bridge is open. This is what I call state desync between the lever and the bridge. The next time I send a signal here, next time I pull this lever, what's going to happen is the door and hatch that's linked to this is going to open, right? Because it's being sent an on signal and it was in the off state. Now, the bridge, on the other hand, is in the on state, receiving an on signal, and so it's just going to be ignored. It's already in that state, right? So these are going to open, these aren't going to do anything, and you can, we've quote unquote fixed the desync problem because the lever is now in the same state as the bridge, but you can see there's kind of this issue where there's not 100% fidelity from our signals being sent to the output devices registering them, right? Some of them have a delay which we need to plan around. A bridge's state can easily desync from a lever's state if you spam lever pull commands fast enough. Similarly, a pressure plate can desync from the bridges it's connected to if its condition is rapidly changed. All right, so just like the pressure plate, or just like the lever, right, a pressure plate can cause these same desync issues. Right, so note, the pressure plate already has a delay before their off condition is accepted, 99 ticks, and added to a bridge's activation delay can result in up to 199 ticks before a room being emptied of water can result in state change. So a bridge being open takes roughly 100 ticks, right? While a bridge closing takes 199 ticks from the moment the pressure plate condition is actually false, right? So it'll take 99 ticks for the pressure plate to go from the on to off state, right? To depress, and then it'll take another 100 ticks for the bridge to open, right? So in designs that need to be extremely precise, right, you need to plan around this, right? You need to plan around this in any case, right? In designs that need to be extremely precise, you need to design around this, right? Usually it won't be matter much because floodgates exist. Okay, now floodgate. So floodgates are interesting to us because they function exactly the opposite way in which bridges work, right? So they block this one-by-one space just like bridges do, except their on state has them as open, whereas the bridge is closed, and their off state has them as closed, whereas the bridge is open, right? So you can think of floodgates as functionally the opposite of bridges. The floodgate has the exact same state properties as the door, except it has an activation delay equal to that of a bridge. And this means the floodgate is the negation of the bridge in terms of state response to signals with the exact same state delay, right? So has a 100 ticks delay, the same as the bridge. So this makes the floodgate, right, functionally equivalent to the door, but 100 ticks slower, and functionally the opposite of the bridge with the same 100 tick delay, right? So this means, we should use the door where possible just because it doesn't have that delay. It'll be faster, just like the hatch cover, right? They're instantaneous. They respond instantaneously to signals. But, where we need to match a bridge, we are going to use a floodgate. All these are on, right? We're going to send an off signal by pulling this. All right, so here's our floodgate, right? You can see it's open when the doors open, and it's going to be closed when the doors close. But just like the bridge, it has this delay when we hit the lever, right? It has 100 tick delay before it's going to change state. Now you can see it is operating opposite to the bridge, right? So when the bridge is blocking water, the floodgate is allowing water, right? And the opposite's true, right? Um, when the floodgate is stopping water, the bridge is going to let water through. Now, so right, this essentially lets us create some interesting things because these are like functionally opposite with the same delay. So I guess one example of this is okay. So this area here is going to be flooded with water, right? We've got a floodgate on one end and a drain, right? So this drains off map. We've got a floodgate that will block water from draining off map, and on the other end of this tube, right here, we have a bridge. So the bridge is stopping water in this large cistern from uh, filling this chamber. Now, this isn't a 1x1 bridge. This is a 1x2 bridge. So when it's down, it's going to block this and let the water go up into this chamber, right? And because the floodgate and the hatch cover, or sorry, the floodgate and the bridge are hooked up to the same lever, they're going to open and close at exactly the same time. So you can see this lever here. It is in the on state. It's pointing left. We've got someone coming to pull it here, and they've pulled it. All right, so they've sent an off signal. It's to the right now. So we've sent an off signal to our bridge and our floodgate here. So we're just going to watch the bridge close. I'm hitting period here to skip forward frames. So when I hit this 100 times, presumably it will close. Or open, rather. This will open, the floodgate will close. There we go. Okay, so this is like one tick after the bridge closed. And you can see the floodgates also closed here, right? And we already have water pressure filling this space. I'm going to hit period, and you can see one frame later, we fill the space way more with pressure, and another frame later, we've hit it even more, right? So this whole chamber is now filled, and you can see the bridge is closed, right? So the water pressure has dropped from this level, right? These tiles all dropped, right? The rest is 7, and over a few frames, they're going to spread out like this. Right? Now the water is going to continue refilling this chamber, but from here, this is where the water comes in. But yeah, okay. I guess the point of this is that whenever I pull this lever, right, this floodgate and this bridge are going to change state, right? They're going to go from on to off in the same frame, right? So this will close in the exact same frame this opens, all right? So we're letting the water in the cistern pressurize this chamber, but the bridge used to open the space is also connected to a lever which is connected to the floodgate that drains the space. And so we can create kind of these interesting enclosed spaces that go from kind of full to empty, right? The on state will let the chamber be filled, and the off state will drain it, right? We don't have to worry about the issues of like the signal timings, right? So let's say I had hooked up this bridge to say these hatch covers. Well, there'd be 100 ticks where the bridge is changing state while the hatch covers are open, and the pressure from the cistern could spill out into these drains. All right, so this kind of system that has an entrance that opens in the same frame the exit closes, or vice versa, is not possible with bridges and hatch covers. I mean, you might be able to make some complicated pressure control system that allows it. I'm kind of thinking about some possible things that could be done just with pressure, but I think clearly the floodgate bridge devices have kind of a natural negation that can be done, which is going to simplify a lot of work for us. Yep, floodgates, very interesting because they are the bridge's natural inversion, right? This lets us do easy negation and lets us create a bunch of, interesting devices. What do bridges and floodgates let us do, right? They provide an easy way to achieve negation, right? Which means they can be used to create two kinds of composite devices. What did I call it before in the table of contents? Oops. Yeah, composite components. Okay, so the first is, right, let's do signal inversion first, right? So, right, we can easily kind of turn an on signal to an off signal using signal inverters. So, you could have one lever pull control two separate entrances, right? So I'll build this in the next part. I'll build a system that does exactly this to control the two entrances of my fort. So if we look at this, go to the surface. All right, so this is the surface, right? This is my trade entrance. This is my trap tunnel entrance. And we can't have one lever easily open one and close the other, right? So we're going to have to create as simple as possible a system that kind of does this, and it's fairly straightforward. But we need these bridges and hatch covers to do it. Bridges and floodgates to do it. All right, so ideally we'll pull a lever and one entrance will open while the other closes. So this would keep their states inverted uh, and simply kind of toggle them both each time the lever is pulled, right? So um, this is what I'll call one version of a signal inverter. Okay, and it's also useful to help us interact with lots of hatch covers and bridges and kind of keep their state synced. So in a previous fort I had this thing in one of the cavern layers where I needed to pump an area full of lava, and some of the things to pump lava in were hatch covers and some of them were bridges. I couldn't have all these set up to one lever because the on signal of one lever would open the hatches while closing the bridges, and the off signal would close the hatches while opening the bridges. When I wanted, both of them to be open. Signal inverters, right? Pretty useful for, this specific use case, right? So, right, signal inverters are useful in two cases. One is where you have two devices that need to have opposite state, even though they're receiving the same signal. And whereas in the second case, right, the we want two separate devices to have different states, two separate kinds of devices. So we'd want the hatch covers to receive the opposite signal as the bridge, right? So in both cases, we're just inverting a set of signals and can be easily achieved with signal inverters. And the other thing that lets us do is what I'll call signal normalizers. So this will turn a lever pull into only on or off signals, for example. We could have a lever that when we pull it in either its directions only has an on signal. So imagine a machine that runs, right, whenever we pull the lever left or right, right? So for example, in my previous fort, I had I automated my obsidian factory. Now the trigger for that automation, right, it would like make a new layer of obsidian every time I pulled the lever left or right. So regardless of the direction I pulled the lever, it would run the machine one time. This is pretty useful, right? Because our levers are sending different signals depending on the direction we're pulling them, it complicates, running a device, for example, right? So another example of this is like a garbage, an atomizer, right? An atom smasher, right? At least when you're running this, like normally off a lever, right? You pull the lever one direction, it closes the bridge, destroying everything, and then you've got to wait a little bit and then pull the lever the other direction so it opens, right? And resets. A signal normalizer would be able to do this in a simple way, right? We would hit the lever in one direction, it would do some stuff. It would like fully cycle the garbage atomizer, right? And then we could pull it in the other direction and it would do it again, right? So we wouldn't have to like reset our garbage atomizer, by pulling it back to the off state every time we ran it, for example. All right, so another example of this exact behavior, right, is with the pressure plate signals. So another case for signal normalizers would be normalizing pressure plate signals. So if you can imagine a pressure plate that's being like walked on by an enemy, right? When it's walked on, it sends an on signal, and 99 ticks after it's not being walked on, it sends an off signal, right? With the signal normalizer, we can transform the signals that kind of system is sending into something more digestible or usable, right? So we could, transform that the on signal only into a pulse of water. We can transform the off signal only into a pulse of water, and then we can also do this kind of thing where either an on or off signal has the same effect. Okay, so this is what I call signal normalization. We're kind of manipulating the on-off signals in a certain way to do certain stuff. That is, one of the use cases for our Floodgate bridge setup. There's one more thing I want to show you. So let's pressurize this chamber, and I'm just going to show you how the pressure plate works, how this latch works. Okay, so we're going to pressurize this room any second now. There we go. We're full of pressure. Now, I've got two levers hooked up to this latch. All right. So the first one on this green tile is one is the latch number. So our latch is 1. It's what I called 1. So this is 1 in. This is 1 out. And we've got our pressure plate, 1 pressure plate, which is hooked up to these 4 devices. All right, so when I open the input, it's going to let water fill this room. When I close the input, it's going to stop water from filling this room. When I open the output, it's going to drain the room. When I close the output, it's going to stop draining the room. If both the input and output are on at once, the water is going to simply pool here, right? And then every few ticks, it's going to let some water onto this tile. But because this is open, it will fall into this U-bend right here, which will jettison it off map. All right, so just run that quickly, and we can see kind of how our pressure plate is going to work. Right, so we have Cogzac is going to hit this lever, right, and immediately this will open, like so. This is pressurized now, and we're going to get water leaking over here. Now this, I believe, was a pressure plate hooked up from 4 to 7. So when the water on top of this hits 4, it's immediately going to trigger. All right, we're at 3, right? 3 out of 7. One more tick, or a few more ticks. There we go. We've activated it. All right, so this is the frame it was activated. You can see the hatch it's hooked up to and the door are open, right? But the bridge and floodgate have yet to change state because they have that delay, right? So in like 99 ticks or something, these will open. Or they'll be sent an on signal. The bridge will go to its on state. The floodgate will go to its on state, which means the bridge will close, the floodgate will open. There we go. Interesting thing about the latch is now that this room is full, right? Opening this entrance, right? Hitting this entrance as many times as we want is not going to do anything. The input for a latch, right, can only fill the room, right? So now that it's closed, the state isn't going to change in this room, right? No matter how many times I hit this, the room is kind of stuck in this state where it's pushing this pressure plate down, right? So that's how a latch is pretty much going to work. So it's just going to kind of hold water and push a pressure plate down until we send it an off signal. Okay, so let's do that. Let's open the offshoot. Okay, so Emush is going to come here and hit our lever, which is going to open this. There we go. Now the room's draining, and there we go. 99 ticks passed, and our pressure plate released. And you can see the door and hatch cover immediately closed, and our bridge and floodgate are going to in a moment. There we go. All right, so that is how our pressure plates work, and you can see how we can control our devices using pressure plates. All right, so this pretty much concludes our section on mechanisms, right? So we talked about doors, bridges, hatch covers, and floodgates in great detail, right? I talked about levers and pressure plates in great detail. We talked about mechanism state versus signals, right? And how our devices are actually sending signals and receiving and changing states based on signals, right? And we talked about signal timings briefly, right? So some devices take some time to one send signals, right? Pressure plates need some time to receive to process their off signal, right? And also some devices have inbuilt delays before their state is changed, right? So this saw, there's some problems associated with this, right? Which is one is desync. We can get desync because of this, and we need to plan around timings is the second thing, right? So design solutions, essentially to deal with the timing differences between the devices. When we are using bridges for something, we should use their opposite floodgates, right? So as not to introduce moments where the important devices in some system have a delay, right? So we would, if we were using bridges and hatch covers, right, the bridges would have like 100 frames or 99 frames before they actually, or 100 ticks, right, before they change state in comparison to the hatch covers, which is a problem, right? So, right, that's pretty much mechanisms. We talked about input devices, output devices, mechanism state, signals, and provided you understand all of this, we pretty much are in a point where we can start talking about composite components and start building some interesting things which will control the logic in our fort. All right, so join me next time, and I'll try to efficiently show you how to make interesting automation in Dwarf Fortress. All right, see you then. Bye.